All right, welcome back. This time we're going to look a little more at gravity fields and some cool stuff about how gravity field is actually a vector. So when you have more than one object creating a gravity field somewhere, that gravity field is the vector sum of the gravity fields from each of the different objects. So that can be a little tricky if there's like a whole solar system where you've got the sun and you got all the planets and another star nearby, and all these things are all creating gravity fields, and there you're out there floating around as a spaceman, and the sum of all of those vectors of gravity fields is the actual gravity field that will be affecting you. And in the solar system, that's mostly the sun. In this problem, we're going to ignore the force of gravity of the sun and the gravity field associated with the sun, and just look at, let's pretend for a minute that the only thing you had was the Earth and the moon. And the idea is they are actually going around the sun together. And so if we ignore the sun, we're just looking at the interactions locally with the Earth and the moon. And that larger question of what you do when you take into account even the galaxy or the galaxy cluster, there's lots of galaxies, and our solar system is actually going around our galaxy, but then our galaxy is also moving around anyway, it can be mind-boggling to think of all of the different movements. So we're just going to look at just this little tiny subset of looking at the moon and the Earth, and ask, well, what if just related to the gravity of the Earth and the moon, what's the gravity field if you were halfway between them? So gravity field is dependent on this equation here where you say little g equals capital G m over d squared. And I'm thinking of it as a d this time. So if I was right here, I could figure out the gravity field due to the Earth. Now, we know here on the surface it's 9.8, and as I get farther away, it's going to get less and less and less. So if I'm halfway to the moon, what is it at that point? It's still not zero. And also on the moon, we could calculate the gravity field on the moon, its surface, which I don't think I had you do yet. But in any case, as you get farther from the moon, it's going to get smaller too. And if we're exactly halfway, I hope your common sense says that, like, oh, well, the gravity field due to the Earth should be bigger than the gravity field due to the moon, which it is because the moon has a much smaller mass than the Earth. So not much smaller, 100 times smaller, roughly. But in any case, what would the gravity field be in the middle? And so let's figure that out. It's pretty plug and chug. The first thing we're going to do is just use this equation twice. So let's use it for the Earth, and then we'll use it for the moon and see what the numbers are. Remember, it was 9.8 on the surface of the Earth. It's interesting when we plug and chug this out, and you're going to put in capital G, mass of the Earth, and then this distance. Where did this come from? Oh, here I am. I'm halfway between the moon and the Earth, and if I'm halfway back here, I forgot to mention that I gave the distance between the moon and the Earth right here, 384,000. So we take that divided by 2, since we're halfway between them. So if you think of this calculation here as a gravity field due to the Earth only, at this location, it's halfway between. I put this red vector going to the right, because that's a gravity field to the right. And then here I recalculate to the moon. So the distance is the same, because this distance here is the same as this distance here, but the mass is different. And so we get about 100 times smaller number here, 0.01 newtons per kilogram. So that's a lot different than 9.8, but that's because we're, really far away from the Earth. We're halfway to the moon, for heaven's sakes. So we get a gravity field that's a lot less. The gravity field at that location due to the moon is much less, and in the other direction, right? That's given by this little tiny vector going to the left. Let me zoom in on this image here so you can see it a little better. If we've zoomed in right here, you can see here's the point in space we're talking about. Nothing actually has to be there to talk about the gravity field at that location. We just have to talk about the location. Put a little blue dot there. So anyway, this gravity field to the right due to the Earth, and this little gravity field due to the left due to the moon make it so that they cancel directionally. And since they're canceling directionally, we would subtract them, right? We would go and just subtract them. So let's see what we get. We get this number, and then we subtract this number. So I kept some sig figs here, 0.01078 minus 0.00013, and I got this, hopefully I did calculator glitch mistake, but makes sense that it's almost as big as the Earth one. It just got canceled a little bit due to the vector going the other way to the moon. Notice this is in a straight line, so it's easy to do that vector math. How you add vectors is you actually make little triangles. So I found this image. It's kind of cute. I guess I should get rid of my picture. It's in the way now. But this shows that it's complicated at all these different locations in space. There's no things here. This is just like, if you were here, what would the gravity field be? This is drawn horribly to scale. But anyway, if you would have like a vector going this way and a vector going this way, you'd have to add them together, sort of like when we did the tug-of-war problems back in the day. So, over here, they're working together. This one's pulling this way, and that one's also pulling this way. So the gravity field, you'd add them together. We're in the middle, so they're fighting each other, so they cancel. If you're over here again, they'd be working together. Over here, you have to draw a triangle because there's this one and that one. And you draw a triangle to find the resultant gravity field. So gravity field calculations get complicated when you go to three-dimensional space with lots of orbiting objects. And anyway, let the computer program do that. As long as we get the idea that since the gravity field is in opposite directions, we're in between these two, that the gravity field cancels, and to get the value, we subtract them. I did put little arrows over the G's this time, and that was just to remind me, to remind you that this thing's a vector, and just like momentum, when you're adding them or subtracting them, you have to think about their directions and cancel them. So these two numbers here are going in opposite directions, so when we add them, you end up canceling, and we get the subtraction in order to figure it out. So that's gravity field due to two objects that happen to be in a line, and hopefully that helps you understand the concept of gravity fields. See you again soon.